something, the little countdown screen seems to have vanished, so you have to just be listening for the little beep. Lesson 3, collisions, car crashes, and conservation of momentum. Now, I have to be honest, Jeff, in Physics 11, all of our car crashes are going to have to be head-on in a nice straight line. In Physics 12, then we can have, like in curling, where you bounce off at an angle, or at a hockey body check where you bounce off at an angle. We just don't have the math skills to deal with it right now. Having said that, even head-on collisions are kind of interesting. Example 1. In the collision seen below between a big truck and a little car, which vehicle experiences the larger force? A, the truck, B, the car, or C, both the same? You know what we're going to do? We're going to vote. You're going to hold your hand up. How high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Dueck will make fun of me if I don't vote, because he's going to remember everybody's face and actually make fun of me if I don't vote. Okay? So you ready? In this collision below, which vehicle experiences the larger force? Who says the truck experiences the larger force? No one. Who says, Dueck, it's obviously the car. It's getting hammered. 1, 2. Who says, Mr. Dueck, they both experience the same force? So you have a choice. You can either defend your answer as being right, or attack someone else's answer as being wrong. Attack or defend? Convince me. Ben.
Defending for C, forces come in pairs.
Oh. Newton's third law. Oh. Can I get a little higher there, Mr. Dueck? How about right click right there? Good enough. Newton's third law. For every action, there is an equal and opposite reaction, which to me is still the stupidest way to phrase that law. I've never understood that. I've told you, Atla, forces come in pairs. It means whatever force the truck applies to the car, Darian, the car also applies exactly the same force on the truck. Okay. The next logical question to ask, though, is, why is it that the car... Oh, I forgot to circle the right answer. The next logical question to ask is, why is it that the car and driver are almost always worse off? Explain. To use mass is a physics word. Explain.
It has a smaller mass and has less time for impact.
Okay. You know what? Let's do our... I disagree with that second part. I think they both have exactly the same time of impact. Because would not this length of time the truck is hitting the car be exactly the same as the length? In other words, if I punch you, the length of time my fist is hitting your face, I think is exactly the same length of time as your face is hitting my fist. Isn't it? So I think time is the same.
The impact zone is bigger.
I think we can go more specific than that. Yeah.
Since the mass is smaller, the acceleration has to be higher, so...
So there's a saying that says it's the fall that kills you, or some people will say it's the impact that kills you. Actually, it's not the force that kills you. It's not the change in momentum that kills you, that does damage. What variable, when we get down to it in fundamentals, is what does damage? Your bodies can't handle big accelerations. You can handle the big force if you have a big mass. That's a small acceleration. If you have a smaller mass, though, you can't handle it. A force does damage, but the reason it does damage is force is mass times acceleration. It's the acceleration that does damage. Now, I don't want to write... how about this? F truck equals F car. Tawny, F equals what? So for a truck, big mass, little a. For a car, little mass, big A. Car has, and the driver inside the car, since you're strapped to the wreckage, larger acceleration. And, okay, then Rob, how can I affect that? Well, acceleration is Vf minus Vi over t. If I can make time last longer, then I can reduce the acceleration. But I think in most collisions, the time of impact is the same for both vehicles. In fact, I think in almost all head-on collisions, the time of impact would be the same for both vehicles. Okay? I need to give you a definition. A closed system is one that's cut off from the outside world. It has no external sources of energy or forces being fed in. Some examples. Frictionless surfaces. What's our best easy example here in Canada of a frictionless surface? Yeah, ice. That means things like hockey and curling can be roughly treated as a closed system. Systems in deep intergalactic space. Again, one of the reasons we were so impressed with Sir Isaac Newton is in the late 1500s, in 1580, he was visualizing outer space. 1580, 1680, 1580, I think it was. Got to double check. He was visualizing outer space with, at the time when even hot air balloons hadn't really been designed yet. Systems floating in the water. Rolling objects. For collisions in a closed system, the contact forces are governed by Newton's third. Forces come in pairs. So the forces are equal and opposite. How could I show that they're opposite, Tawny? Negative. That's also why I knew I was doing this lesson. That's why I emphasized it in the example that you and I went over. Now, here's what that means. If the forces are the same, and I've just told you that the time of impact are the same, that means that the impulse, fancy word for impulse is change in momentum, is also equal and opposite. Let me prove it. Okay? Forces come in pairs. That's Newton's third law. F1 equals negative F2. Check. I'm telling you, Rob, that in a collision, they both have the same amount of time of impact. So I'm going to multiply each side by time. And hey, force times time is change in momentum. Force times time is change in momentum, but the fact that there's a negative just means it's in the opposite direction. What we're really saying is whatever momentum one object lost, the other object gained. What does it mean to say that momentum is equal, change is equal and opposite? If the car loses 20 units of momentum, 20 kilogram meters per second, what happens to the truck? It gains 20 units of momentum. What that means is, since the momentum change is equal and opposite, the momentum for the whole system, for the both car and the truck, or whatever collision we're looking at, is neither gained nor lost. It's transferred from one object to the other. Similarly, in the same way that energy was transformed from one form to another, that gave us the law of conservation of energy. Turns out there's also going to be a law of conservation of momentum. Turn the page. Wait a minute, Mr. Dueck. Wait a minute. If you're telling me that the car and the truck end up at rest after the collision, which I would argue, Kai, in almost any collision, that's what happens, which means what's the final momentum in almost any collision?
0.
What that means is the initial momentum must have been 0. Wait a minute, Mr. Dueck, you got stuff moving. How can the initial momentum be 0? Because you've just told us the momentum is mass times velocity. Yes, I have. So I wrote here, if conditions are such that the car and truck end up at rest, how can we say that momentum has not been lost? So after, momentum final is definitely 0. It is. What's momentum initial? Well, momentum initial is momentum of the truck and momentum of the car. But you know what? I've been sloppy. I should remind myself that these are all vectors. What did we say momentum was? What times what? Not force times change in time. That's change in momentum. Just plain old momentum, the very first equation we did for this new unit. Momentum, yep. Mass times velocity. You don't have to memorize that. You probably will because you get sick of looking it up. Okay, momentum is mass times velocity. So really, the momentum initial is mass of the truck velocity of the truck plus mass of the car, velocity of the car. Wait a minute, Mr. Dueck. How the heck can you add two things together and get 0? Let's find out. Let's try plugging in some numbers. The initial momentum equals, what's the mass of the truck? 2,400. What's the initial velocity of the truck? 10 plus. What's the mass of the car? 1,000. What's the velocity of the car? It's not 24. The speed of the car is 24. What's the velocity? Has to be. Because you decide, as soon as Atlas said the velocity of the truck was 10, what he'd really decided for the rest of this question was, I guess to the right is positive. You don't need a calculator for this. I think you end up with 24,000 plus negative 24,000. I can do that in my head. What is 24,000 plus negative 24,000? Ben?
0.
The final momentum was 0. Why? Because the initial momentum was 0. There was kinetic energy, yes, but in terms of momentum, there you go. This is the law of conservation of momentum. Curtis says this: in any collision or explosion, in fact, here's what I teach my physics 12s. In my physics 12s, I say, is there a change in height? Is there a change in speed? That's a job for conservation of energy. Is there a collision? Is there an explosion? Is there a jeune? That's momentum. So collision, explosion, momentum. That's a job for conservation of momentum. Okay? Rosanna is laughing. Oh, the sir was a nice touch. Fine. You're also going to be driving slow through school zones for the rest of your life, aren't you?
I sure am.
Mr. Dueck made a fake RCMP phone call to her yesterday morning to wake her up.
It was not good. I was shaking.
It was good. It was great. Did it on speakerphone in front of the whole class. It was awesome. In any collision or explosion, and by a closed system, what I mean is, Anthony, don't have a third car come crashing in, or don't have somebody pushing something, or don't have the engine suddenly start speeding things up. A closed system, no outside forces or energy source. Momentum is conserved. And what was the word conserved a fancy word for? The amount before equals the amount after. Momentum is not created, it's not destroyed, it's transferred from one object to the other. The law of conservation of momentum can be written in several ways. Okay? The first way says momentum of object 1 initial combined with momentum of object 2 initial equals momentum of object 1 final plus momentum of object 2 final. The second way is the fancy physics 12 method, because we get really complicated questions with multiple objects. Does anybody know what that symbol, actually, when you type it, it looks like that, but when you handwrite it, we usually just go like that. What that is an abbreviation for? Sitting right there. It's a Greek letter epsilon for those of you who keep score. Okay? It's a handy one. You'll probably learn it next year in grade 12, and you use it all the time in university as well. It's an abbreviation for the sum of, or the total. So you can imagine if you're in a class where your prof talks a lot, you start to pick up all sorts of abbreviations if you're trying to write down what the prof says, and one of them is, that becomes your abbreviation for the word total, or add them up, or sum of, or whatever. Okay? So this is saying if you add up all the momentum before, initial, that equals all the momentum after, final. This is the one I tend to start with, even though it looks intimidating. I always write this down, and you'll see why in a second. Or you can break it down that way. It's easier if we do a question. Example. A 1.5 times 10 to the third kilogram car traveling 44 meters per second collides head-on, wham, with a 1 times 10 to the third kilogram car traveling 22 meters per second. You know what? I'm going to underline in the opposite direction. If the cars stick together on impact, what's the velocity of the wreckage after the impact? So we're analyzing car crashes. Okay? I gave a hint. I said make sure you let the velocity of the second car be negative in the opposite direction. All right. Is there a collision? Read the question. Is there a collision? Yes? This is a job for conservation of momentum. And so I always write down the sum of all the momentum before has to equal the sum or the total of all the momentum final. Write that down. That's my, just like when there's a change in height, change in speed, right away I wrote down conservation of energy. Is there a collision? I go here. And then I usually tend to drop the equal sign down. Before the collision, what's moving? Mass 1, mass 2, or both? Read carefully. Before the collision, what's moving? Mass 1. Oh, you know what, Jeff? Let's decide from now on, the first mass that appears in the question, I'll call mass. And the second mass that appears, I'll call that mass. Let's just all do that so all our work looks the same. You could call, if you wanted to, this mass 2, and you could call the car mass 1. Or you know what? Come up with a system that works for you. My usual tendency is whatever shows up first is mass 1. Makes sense to me. So before the collision, what's moving? Mass 1, mass 2, or both? Sorry? Both. Stuck together or separate before the collision? Separate. So here's what I write. The momentum of the first guy before the collision, P1 initial, and the momentum of the second guy before the collision. Wham! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Read the question carefully. Both. Stuck together or separate? Okay, this is the procedure you're going to do every time if there's a collision. Before the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? After the collision, what's moving? Mass 1, mass 2, or both? Stuck together or separate? Stuck together, so that's going to be the momentum of both final. If they were separate, I'd have momentum 1 final plus momentum 2 final. So I always start out with that summation. It looks a little weird, but that's my way of reminding myself, look at the beginning of the question, find anything moving momentum. Wham, they collide. Look at afterwards, find anything moving momentum. Okay? Momentum is what times what? Mass times. So momentum of object 1 is going to be mass 1 V1 initial. Yeah? And plus? How would I write the momentum of object 2 initial? Mass 2 V2 initial. Is that okay, Jake? Wham, they collide. How would I write momentum of both? Oh, mass 1 plus mass 2 V final. If they're stuck together, they must be going at the same final velocity. That's the definition of stuck together. Okay? Now, you cannot, Zach, memorize this third line and just start there. You can memorize the second line because every collision is going to be different. But you can always start with the very first line by saying, is there a collision? This is a job for conservation of momentum. Everything before that was moving, stuck together or separate, has to equal. By the way, what if they've been stuck together before? It would be momentum of both initial. I have to move over here now. What are we trying to find? Which one? There's 3 in my equation. Sorry? How would I get V final by itself? Divide by the bracket. I mean, it's a little uglier, but we've kind of seen stuff like this before. So if I hear you correctly, the final velocity is going to be M1 V1 initial, M2 V2 initial, divided by the bracket. Now, that's a little ugly, but it is plug and chug. I mean, fairly ugly plug and chug. Let's be careful. Let's see. So the final velocity, and again, notice I'm really being careful with my vector notation to remind myself, be careful, be careful, be careful with directions. Read, what was mass 1, my friend? As a number. Just 10 to the third? I think there's something in front of the for the third. 1.5 times 10 to the third. In fact, I think that's 1,500, which is less typing. So 1,500. Read, my friend, what's V1 initial? Yep. Keep going. What's mass 2? Hey, nice 1,000. 1 times 10 to the third. What's V2 initial? Don't say 22 because it's not. Ah, opposite direction. All over 1,500 plus 1,000. Is there more than one number on the top? I better put brackets around the top on my calculator. Is there more than one number in the bottom? I better put brackets in the bottom on my calculator. I think the final speed, the speed that this wreckage will move off at is bracket 1,500 times 44 plus 1,000 times negative 22, close bracket, divided by bracket 1,500 plus, I probably could have just put a 2,500 down there and added them up in my head. That's fine too. By the way, if I get a positive answer for the final velocity, that means relative to mass 1, the whole wreckage moved forward. If I get a negative answer, that means relative to mass 1, the whole wreckage moved backwards. If I get 0, that means by a fluke, they collided and came to an exact stop. 17.6, right? I guess what happened is this. Bigger car, smaller car, they came towards each other. Sorry, let's do a better collision. They came towards each other. They slowed down, but they continued moving in the direction of the bigger car. Okay. Skateboarder, another person standing on a skateboard. Let's see here. A 53 kilogram skateboarder on a 2 kilogram skateboard. You know what? This is going to be mass 1, and I guess mass 1 is a total of 55 because it's the skateboarder plus the board. Is coasting along at 1.6 meters per second. He collides with a stationary skateboarder of mass 43 kilograms, also on a 2 kilogram skateboard. I guess M2 is going to be 45 kilograms. And they coast off in the same direction that the first skateboarder was traveling. I think they would. What velocity will the combined skateboarders now have? Oh, let's try that again, Mr. Dueck. Halen, what word did I underline? Did you say there's a collision? This is a job for conservation of momentum. The amount of momentum before the collision equals the amount of momentum after the collision. Total before equals total after. Before the collision, what's moving? Mass 1, mass 2, or both? Read carefully. Just mass 1? Momentum 1 initial. Wham! They collide. After the collision, what's moving? Mass 1, mass, yes on every question, Michael. After the collision, what's moving? Mass 1, mass 2, or both? This I can't help you with. This you just got to read. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? how would I write momentum 1 initial? Why, that would be mass 1 V1 initial. Wham, they collide. How would I write momentum of both final? Mass 1 plus mass 2 V final. Don't forget the vector symbol, Mr. Dueck. Manny, my friend, what's this question asking me to find? Nice. How to get V final by itself? Yeah, nice. This isn't so bad. So if I hear you correctly, Manny, and I think I do, you're saying it's going to be M1 V1 initial divided by M1 plus M2. Before we start crunching numbers, look at this expression here. By the way, you can think about this as tackling somebody as well. It's the same physics, okay? Suppose the girl, the second person, mass 2, was heavier, had more mass. What would their combined speed be? Bigger, smaller, or the same? Atla. So, yeah, if you divide by a larger number, you're going to move off small, which kind of makes sense. If this was like, for example, if this person, if the skateboarder, instead of hitting a person, hit like a cement block, they might barely be moving afterwards. Okay? What if this person was going faster initially? What if that was bigger? They'll move off together at a bigger velocity. So just letting you know, and that makes sense. If I go faster and I hit something and I grab it, we move off together with more speed. Okay, that makes sense too. But just want to see that the physics works too. I've scrolled down. What was mass 1? 50-something. 55? What was V1? Mass 1 was 55. What was mass 2? 40? 40? 45? Bracket 55 times 1.6 divided by bracket 55 plus 45. That's 100 in the bottom. By the way, should my answer be bigger or smaller or the same as the 1.6? After they hit, will this guy speed up, slow down, or stay the same? Slow down. I'm expecting a smaller answer. Oh, 0.88. Almost slows down to half the original speed. A little more still. Turn the page. Let's fire a gun. Now, a gun is an explosion. Did I say explosion? That's also going to be a job for conservation of momentum. A .06 kilogram rifle bullet leaves the muzzle with a velocity of 6 times 10 to the 2 meters per second. If the 3 kilogram rifle is held very loosely, with what velocity will it recoil? So now we're imagining firing a rifle. Okay? This is an explosion. This is a job for conservation of momentum. I can write this. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Or in this case, the explosion. All right. Before I pull the trigger, what's moving? The bullet, the rifle, or both? It's a trick question. Nothing. Nothing is moving? So what's my initial momentum before I pull the trigger? 0. What's my final momentum after I pull the trigger then? Has to be 0. But I think I'll break that one down. But certainly before I pull the trigger, my initial momentum on the bullet rifle system is 0. Bang! The gun goes off. Really, Darian? Okay. After the explosion, what's moving? The bullet, the rifle, or both? Stuck together or separate? Oh, so I'm not going to do both. I'll do them separate. You know what? Instead of going mass 1 and mass 2, how about B for bullet and R for rifle? I'm going to go like this. Momentum of the bullet plus momentum of the rifle. Okay. Momentum is what times what? So I guess momentum of the bullet final is going to be mass of the bullet, V of the bullet final, plus mass of the rifle, V of the rifle final. Hey Manny, you did so good last time. What are they asking me to find this time? There's two velocities. Which one? There's two V finals. Which one? Now I'm saying, read the question. They're either asking me to find how fast the bullet's traveling after I pull a trigger or how fast the rifle recoils after I pull a trigger. Which one? Oh, so they want me to find VR final. Yeah? Okay, let's get that by itself. I think the first thing that I would do is I would minus this whole thing over to that side. And since there's a 0 over there, I think I'll get this. Negative MB V bullet final, negative mass of the bullet, V bullet final, equals mass of the rifle, V rifle final. Is that okay, Halen? I just minused it over. Okay, keep going. How would I get the V rifle by itself?
Divide by the mass.
Which one? There's two masses. More specific.
Mass, right?
Yeah.
Right.
So if I hear you correctly, you're saying, Mr. Dueck, the final velocity of the rifle is going to be negative mass of the bullet, V of the bullet, divided by mass of the rifle. Okay, let's crunch that. Negative 0.06, that's the mass of the bullet. 600, 6 times 10 to the 2, that's the final speed of the bullet. All over 3. This time I don't have two masses down there because it's not mass of both. Okay. Now I'm going to get a negative. What's that telling me? If the bullet is traveling to the right, which way will the rifle recoil? To the left. If the bullet is traveling south, which way will the rifle recoil? North. If the bullet is traveling west, which way will the rifle recoil? East. Which the word recoil implies that, but there, it's telling me, by the way, as a vector, this velocity has a negative, and it comes out of the physics. Mr. Dueck, negative 0.06 times 600 divided by 3. I probably could have done this in my head. I'm thinking 36? No, wow, way off. Of course, you're dividing, Mr. Dueck. Negative 12 meters per second. So if I were to actually bang and fire this, I'd have to brace my shoulder because whatever momentum that I give to the bullet going that way, the rifle's going to absorb going this way. I have to absorb it. What if it was a higher powered rifle with more gunpowder and a heavier bullet? More kick. 22 rifle, small bullet, small speed, you barely feel it. Bigger rifle, more kick. I used to work at a summer camp, and one of the things I taught was canoeing. And every year I would see something like this. So Enzo is sitting on a canoe. Here we go. Mr. Dueck in his canoe. Next to the dock, he decides to stand up, and then he's going to step onto the dock. What happens? Before he starts to move, what's the momentum of him and the canoe. 0, because no one's moving. If he applies the momentum to his right, and the momentum still has to stay at 0, what's the only thing that physics allows to happen? The canoe has to move to the... He's going to end up doing the splits and go into the water. I saw it happen time and time and time again, and I would just laugh. Right. Any of you canoe? Okay, so if you ever do, how do you get out of a canoe? You stand straight up, momentum 0. You pivot, momentum 0. You sit down on the dock, momentum still 0. Then you can lift your legs up and out. Keep one hand between the dock and the canoe if you want to. Or, if you insist on stepping, then the other thing is people think, oh, I'll just grab and I'll pull the canoe in with my off hand. Problem is a little more force there than you realize. So be careful. Or get wet. 15 years ago, it was funny. Nowadays, everybody has a cell phone and it's expensive. 15 years ago, when you fell in the water, nothing got shorted out. So, why does Enzo get wet? I'm not going to write out the whole explanation, but you guys followed it, right? Okay. Initial momentum is 0. Your final momentum has to be 0 if you decide to move to the right. Or the other one, how many of you ever tried when you're horsing around in the water, tried standing up on an inner tube or a floating, and then when you dive forward, what happens to the thing that you were standing on? Shoots backwards out. Why? You wanted to apply momentum forward. You're starting with a momentum of 0. What you're standing on has to move backwards to keep the momentum 0. And since it has a way smaller mass than you, it's probably going to shoot out faster than the velocity you were hoping to generate diving forwards with your feet. Really? It's not just that I'm not athletic? No, it's a physics thing. You can't do it. Let's go to outer space. So a 4,000 kilogram space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe, like the lovely picture there. The space vehicle is traveling at 120 meters per second when an explosion occurs. But, well, it could be a deliberate explosion. This is how they did multi-stage rockets. Although looking at the picture that looks fairly jagged, maybe it's a bad explosion. After the explosion, the probe moves forwards at 280 meters per second. Okay. A says, what's the new speed of the main capsule after the explosion? After the what? Did you say explosion? This is a job for conservation of momentum. The sum of all the momentum before the explosion equals the sum of all the momentum after the explosion. The total momentum before equals the total momentum after. Before the explosion, what was moving? Mass 1, mass 2, or both? Stuck together or separate? So I'm going to end up with momentum of both initial. Boom! Explodes. You looked at me. I thought we made eye contact. I thought you got my... no. Okay, sorry. I thought you'd made eye contact with me. I was like, good, he got it. You saw me staring, right? Anthony? Yeah, you figured, okay. Darian, after the explosion, what's moving? Mass 1, mass 2, or both? By the way, are you seeing, it's not exactly repetitive, but the strategy is going to be the same. I just don't know what the situation is. Both stuck together or separate? So it's going to be momentum of object 1 final, momentum of object 2 final. Oh, this is going to be a fun unit for me. And for some of you. All right, let's break momentum down. Mass times velocity. So I guess the momentum of both would be the mass of both. I'll call that m1 plus m2 v initial. And then the momentum of one final is going to be mass 1 v1 final plus mass 2 v2 final. What did this question want me to find? Trevor, what did this question want me to find? Okay, I've called this mass 1. I've called this mass 2. So you know what? Yeah, it wants me to find that. Okay. Little trick here, but how would I get that by itself? First, I need to deal with this second term. Trevor, how could I move this second term over? Why subtract and not divide? What's in front of the m? Plus, so subtract. So I'm going to get this. M1 plus M2 V initial, take away M2 V2 final. That equals M1 V1 final. Keep going, Trev. You're saying, hey, Mr. Dueck, do that? Okay. I think you're right. By the way, what if I get a negative answer here? It means that when the explosion occurred, they're both moving forwards, the explosion occurred, boom! This guy went shooting forwards really quick. Maybe this guy got shot backwards. I don't know. I haven't done the math yet. But if I get a negative, it's possible. I need to know the dynamics of the explosion. So V1 final is going to be mass. I need the data. Scroll up, Mr. Dueck. Mass 1, 2,500. Mass 2, 1,500. V1, 120. Take away 1,500 times 280 all over 2,500. It's worth practicing these on your calculator, Mr. Dueck says. Hint, hint, hint. Bracket. Oh, and then you know what? I need another bracket. 2,500 plus 1,500 times 120 minus 1,500 times 280 divided by 2,500. Is that right? Bracket, close bracket. I got the top in brackets. I got a little mini bracket in the top, but I closed that off. All divided by only one number on the bottom, so no need for brackets on the bottom. I think, is that right? Yeah. Yeah, 175? Wait, 175? No? People shaking their head? Maybe I'm wrong. Oh, I'm missing a 0, Mr. Dueck. Here, I'm looking at my work. Let's try that. 24? Did they ask speed or velocity? Okay, if they said velocity, then I would say something like in the same direction or some kind of a vector component like a speed. Okay. Ah. What does B want me to find? What's another word for impulse? Okay, so it wants me to find the change in momentum of mass 2. Of the probe. Am I going to use the change in momentum that's got final and initial velocity in it, or am I going to use the change in momentum that has force and time? You focused, or I shall yell again. You hear, Darian? Yes? Someone out in the hallway. Sorry? Yeah, they didn't give me a force or a time, so I think I'm going to use the mv final minus mv initial. Which m? Mass 2, mass 2. Okay. The change in momentum on the probe, the impulse. Mass 2 was 1,500. Final 280 minus 1,500. 120. You get 240,000? Yep. Units. Kilogram meters per second. If you have room, we're going to add a part C. What was the impulse given to the... It's not the capsule. What was it called? Oh, yeah, the capsule. No need to do any arithmetic or any math. Kai, what was that? I gotta be fussy. You're close, but not quite right. Why negative? Did the probe gain momentum? Did the probe gain momentum? Yep. So what? The capsule had because momentum is conserved. Negative. And again, in this case, the negative both connotates a direction in the opposite direction of the probe, or you can think of it as a loss. It lost that much. The probe gained. Also, I noticed the capsule slowed down, because wasn't the capsule's initial speed 120, final speed 24? Yeah, it lost a lot of momentum. Couple videos to show you.